All right, so Pythagorean triples, a set of three positive integers that satisfy the Pythagorean theorem. This section will deal with the problem of finding the three integers that can represent the legs and hypotenuse of a right triangle, a triple of numbers satisfying the Pythagorean theorem. The primitive triple is a non-reducible triple, right? No common factors other than one, right? A, B, and C are relatively prime, so another term for that would be coprime. So there is no factor other than one that is in common between or among the three values that make up the triple. Right. The creation, we have Euclid's formula. Right. That's the first method. Then the Liberi method, right, which we can talk about in a little bit, and then we'll get into where I'll give you the opportunity to work on those practice problems. So Euclid's formula, a is equal to u squared minus v squared, b is equal to 2 times uv, and c is equal to u squared plus v squared. All right. So the u and v values have to be of different parity, meaning one is even, one is odd, and relatively prime. So again, only common factor between or among the values would be 1. Right. And so if that's the case, then we would have a primitive Pythagorean triple, which is ultimately what we would like to find, which serves as the basis of a whole system of Pythagorean triples that are related to it. All right, so for example, this is a triple 3, 4, 5. It is a primitive triple. All right, if I did 6, 8, 10, that's 2 times 3, 4, and 5. All right. So 3, 4, 5 serves as the basis for another triple 6, 8, 10. Let's say 9, 12, 15 is 3 times 3, 4, 5. All right. So I could have 3n, 4n, 5n, which would be n times the values 3, 4, 5. All right. So this ends up being an entire system of possible. So this is the basis of a system of triples. System of triples. And this would be the system of triples. Triples, not Star Trek. Triples. All right. When we want to identify a Pythagorean triple using particular u and v values, we have to first make sure that u is greater than v, and that only has to do with the nature of the rule. All right. So u and v have to be positive integers, and u has to be greater than v, because if u is less than or equal to v, if it was equal to v, then I would get the a value equal to 0. Right, and if we're talking about legs of a right triangle, if one side is equal to 0, that doesn't really work. Right. The other possibility is if a is less than v, then I would be looking at a negative a value, which, like I was saying in the previous video, there is a school of thought that allows for negative sides. It's just not this area. Right. So if I'm given particular values of u and v, I could use my rules here. So I'll just do it off on the side here. A squared is equal to, right? So, a. I'm not at the point where I'm going to actually test it out. So u squared minus v squared. The b value, again, 2uv, and then the c value is u squared plus v squared. All right, so for a, I'm doing 10 squared. And we've verified u is greater than v. Both u and v are positive. All right, so 10 squared minus 6 squared. So that's 100 minus 36 is 64. We'll get into actually testing it out in a minute. Let me just do it like this. I put a 39 in there for some reason. There we go. All right, the b value would be 2 times 10 times 6. That's going to be 120. And my c value would be 10 squared plus 6 squared, 100 plus 36, so 136. All right. So the A, B, and C values are found, and that would give us a Pythagorean triple. But like I said before, I'll verify that for you, because A squared plus B squared should be equal to C squared. So 64 squared plus 120 squared should be equal to 136 squared. I take my square root, and I get 136. So it does check out. All right. So if you're given two particular integers, then we could determine whether those, or determine a Pythagorean triple based off of those two positive integers. All right. The other thing that we might be asked to do is to determine if it's a primitive value. All right. So in this case, so again, the A and the B values, we would be looking to see if there were a simpler form of this. So there really are a couple of ways to do it. One way would be to just base it off the U and V values. The other would be to actually look to see if you could take the numbers and divide them by 2, for example. All right, so 64, I could make a 32, a 60, and that would be a 68. So I'm just chopping these three numbers in half, my A, B, and C values. Right. It's a quick way. If they're all even, then it should work. So I would check to see if this is also a set of values that would satisfy the Pythagorean theorem. And it does check out. All right. So I could go further. So 16 squared plus 30 squared is equal to 34 squared. All right. Still even. 8 squared plus 15 squared is equal to 17 squared. So this is more of a trial and error approach. Now I see I get to a point where I can't divide anything by 2 anymore. Right? I would be looking for a greatest common factor that I could divide out. So I might try one of the features in this calculator under arithmetic is the greatest common divisor. So I try 8 and 15. I can never remember if it lets me put a third value in here. I'll give it a shot. And it says 1. So if the greatest common divisor is equal to 1, then that means that they're relatively prime or coprime, right? Which means that the basis would be 8, 15, and 17. And the system of triples would be 8n, 15n, and 17n. Right, where n would be some sort of, you're not really limited to whole number values, as long as there's a common multiple. So let's say I had 8.5, sorry, not 8.5, let n equal 1.5. So 8 times 1.5, 15 times 1.5, and 17 times 1.5. So 12 squared plus 22.5 squared, square root, and you get 25.5. Right, so we would just need n to be some value that's greater than 0. So I would just make a little note that n has to be greater than 0. All right, so that's one way to do it in terms of determining whether or not it's primitive. But if the u and v values themselves, right? So just going back to the u and v values, the ones that we started this whole process with, if they are of different parity, meaning one is odd and one is even, and relatively prime, right? So they only share the common factor of 1, then the triple that you generate will be primitive, all right? I just want to check. Yeah, so the next example actually has that. So my u and v values, right? The integers are 1 and 2. Now u has to be greater than v in order for this to work. So I would designate my u value 2 and my v value as a 1. All right, so the greatest common divisor between 1 and 2, probably shouldn't need a calculator for that, but in case you do, the result is going to be 1. So they are relatively prime. All right, that's the first condition that needs to be met. And they have different parity. And again, parity is just talking about being even versus odd. All right. So we meet both of the conditions here. So now I would figure out my A, my B, my C. So 2 squared minus 1 squared, 2 times 1, 2uv. And then u squared plus v squared, so 2 squared plus 1 squared. So 4 minus 1 is 3. Result 4. 4 plus 1 is 5. All right, so that would be a Pythagorean triple. And it would be a primitive. Three, 4, 5. All right. So I don't have to test for it after the fact. All right. So if I check my conditions and they're met initially, then the resulting expression will be a primitive Pythagorean triple. All right. Now the Libri method. So, and it's optional, but it's interesting. If m is a natural number greater than 1, then a divided by b is going to be equal to 1 over m plus 1 over m plus 2. And the c value will be equal to the square root of a squared plus b squared, where a, b, and c would be a Pythagorean triple. All right. So this is it's not using u and v, so it's different, but it'll amount to essentially the same thing. All right. So find the Pythagorean triple using m equals 2. So I would have, again, a few different things going on here. I would have a over b is equal to 1 over 2 plus 1 over 2 plus 2. All right. So that's going to be a over b is equal to 1/2 plus 1/4. All right. So I have a ratio of a and b, which allows me to do a substitution if I want. All right. But it also gives me a relationship between the value of a and the value of b. All right. So it's basically saying that a to b is equal to whatever that fraction ends up being. In this case, it's 3 over 4. So we could look at it as a to b is equal to 3 to 4, which means really any multiplier of that would work. All right. So if I want to let that multiplier be equal to 1, then I'm good. The c value. So I'll just write it as equal to 1. So if I want my multiplier to be 1, then my C value would be equal to, again, the square root of a squared plus b squared. 9 plus 16. C would be equal to the square root of 25, which is 5. All right. So I would have a triple out of this, and this would be a primitive triple, because if that multiplier is just a 1, then that would be the only common factor between, again, they meet the requirements, even though it doesn't really explicitly say it in this method. If it meets the requirements of having different parity and of being coprime or relatively prime, then it would be primitive. So I have the 3 to 4 to 5. Would be the primitive Pythagorean triple, and any multiple of that. So when it says find the Pythagorean triple using m equal 2, that would be the primitive Pythagorean triple, right? So now it's saying to do 5 sets for all m values between 4 and 8. I might not do all of them, but I'll do an example here. So let's say we had I'll just pick something in the middle, like a 6. All right. So a over b would be equal to 1 over 6 plus, again, the rule is 1 over whatever your m value is. So I'll make a little note here. M is equal to 6. And 6 plus 2. So 1 over 6 plus 2 is 1 over 8. All right. So if I add them together, I'll use a calculator here. I get 7 over 24. A over b is 7 over 24. So again, if I want to write that as a ratio, a to b, 7 to 24. All right, there is no common factor other than 1 between the 7 and the 24. All right. And they're of different parity, or a disparity. One's even, one's odd, so we're good there. So C would be equal to the square root of 7 squared plus 24 squared. So 49 plus 5, 76, I think. I'll just put the whole thing in. Gives you a result of 25. So 7 to 24 to 25 would be the basis of this system of triples. So any multiple of that. So if I did 14, 48, and 50, 14 squared plus 48 squared, square root of the 2500 would be 50. All right, so that's just a quick example, but I wanted to give you something here, because be a fairly lengthy video if I were to do all of the values between 4 and 8. But and it does say to find 5 sets of Pythagorean triples. So, like I could double, like I did 14, 48, 50. I can triple 21, 72, 75. I could multiply by 5 if I want, so 35. 120, I think, and 125, multiply by 10. Honestly, if you really want to just kind of bang through it, you could just multiply by 10, by 100, just keep tacking on zeros, you'd be good. It would satisfy the requirements, but, something like that. And then I would do it again for, I already did it for 2, but then I would do it for 4, 5, 7, and 8, all right? So it would take a little while. But that should set you up for 4.1, the section on the Pythagorean theorem. All right. It seems lengthier than it is, but only because of the diagrams and the setups for some of the problems.